Welcome back, gang. We started this semester with a discussion into this idea that when we talk about numbers, ever since elementary school, we have been dealing with these mathematical objects we call numbers. But our elementary teachers hid from us one critical fact about our universe, which is absolutely astounding, and that is we cannot actually see numbers anywhere in the world around us. Numbers aren't running around in a forest somewhere. We can't perform studies on these things called numbers. And so, while this seems obvious to us now, the problem is if we say something is true, we have to then explain how we know something is true. And in mathematics, if we want to be rigorously dealing with the truth in the sense that when we are manipulating these equations, uh, we're manipulating these equations only insofar as the manipulations themselves will yield an answer that is coherent, right? We're not arbitrarily introducing new terms into an equation. We're not manipulating an equation outside of the rules of algebra in some way, shape, or form that wouldn't make any sense or that would be incoherent. Instead, what we're doing is we have a system, a methodology, if you will, by which we can do rearrangement on a formula and obtain an answer every single time we do it. And so, but the problem is if we're not able to actually view numbers in the world around us and we're not actually able to run an experiment on them, how do we know that these numbers actually exist? And if if they exist but they're not material, then what does that mean? Well, if things exist, and to the extent that anything can exist, which is made up of immaterial items such as numbers or shapes such as a triangle. There's no such thing as a perfect triangle in the world around us. There's no such thing as a perfect square or a perfect rectangle in the world around us. No, these ideas come from math and geometry, but they're not actually in the world around us. It's that our eye perceives something that is rectangular. Our eye perceives something that is triangular. It's not that there isn't triangle in the world itself, right? And so, to the extent that these things do exist, we're left with just saying that these items must exist in some sort of a state that is beyond what we understand with our physical senses, or what we can comprehend with our physical senses. So if numbers are a thing, and we assume that they are because we've been using them for so long, and it seems to be true, in other words, it would be incoherent at this point to say that numbers are not real, or that it's an opinion that numbers should exist. Okay, that's kind of an incoherent line of thought that would not comport with our experience for the last, 10 years of our life or so. Um, then we must simply state that numbers exist beyond ourselves, or are some sort of what we call metaphysical, or they're a transcendent something. They exist in a transcendent reality if they are indeed real themselves. And so, and what this actually implies about the universe around us is that if you were to create, say, bubble diagrams, the physical world that we know, that we're able to understand, that would be in the middle of the diagram itself. We would say that's the corporeal, that's the physical reality that we find ourselves in. And then, because math exists in the sense that we're able to represent it on paper, but then it also transcends this physical reality, we might say have an arrow that is drawn between the bubble representing the material world and the bubble that represents everything that exists beyond the material world, in this transcendent space where math is a thing that is real in the sense that physical objects are real. And then beyond that, we would have a bubble that represents all possible truths and all knowable truths that we simply, because we're trapped in a physical universe, We don't have any way of, say, knowing what exists in this transcendent realm in any concrete way, shape, or form. At least, we may have ways of coming to know certain things or certain aspects of this transcendent realm, but it to the extent that we can do that, it's often insufficient and or lacking in the preciseness of, say, science. Okay, and so we would have this bubble around all of these metaphysical things, and that would represent all of possible truth that you could know about the universe as a whole and everything outside of the universe. Okay. And so um, it turns out that the first man to really expound or bring this idea to the forefront in mathematics was a man named Rene Descartes. And this week because we're learning about the Cartesian coordinate plane, we're also going to be learning about where it came from and why it exists. And so um, Rene Descartes, although he's often claimed to be the person who invented the Cartesian coordinate system, wasn't actually the inventor of the Cartesian coordinate system, but instead he was a philosopher and a geometer and an algebraist who was foundational in bringing together multiple different ideas that had existed in philosophy in ancient antiquity, specifically bringing together Platonism and what is known as Aristotelian thought, Aristotelian logic, and melding these two thought paradigms together in a single work called The Meditations and Discourses on the Method. Okay. And then he in the meditations, he's discussing how we come to know what is truth. And then in discourses on method, he's discussing all of the ways that you can know that something in our physical universe is actually true itself. And so the scientific method didn't actually always exist, right? It's this phrase that we use to describe the process that a scientist goes through when he's applying what is called the empirical system of thought or system of rigor. But this idea of empiricism didn't always exist. And so what you really see in the 1560s is these mathematicians and these early physicists such as Isaac Newton, and Fermat and Rene Descartes. They're actually the ones who get together and start to bring to the forefront this idea that you can view the world around you and then perform studies on the world itself and come to know things from that. So discourses on method and meditations are these two very interesting philosophical works. And then what's important for this class is a book called De Materia de la Géométrie, which is his work on geometry. And what Rene Descartes does do is he takes the medieval what was known as medieval geometry and the ideas that were really being passed down since the time of the Greeks, um, and he converts that into the works of algebra. And so he's able to, say, take some of the discoveries that were coming out of Arabia in the 7th and 8th and 9th century that were then passed to the Italians in the 11th century at some point in time, and which were steadily improved upon until the 1540s. And he kind of brings all of this together into one single spot. And because of this, he is often attributed as being the person who created the Cartesian coordinate system, although you never actually see it in his work, the geometry. You do see things that are very close to a Cartesian plane, but what's more interesting is that Rene Descartes was he liked to study geometry, and he determines that as long as you're able to phrase a problem statement in the terms of geometry, it turns out that there will always be a algebraic solution to that geometry problem. And this is great because in the medieval period, you had these really, really super complicated geometric proofs, but if we can take the geometry ideas and we can instead represent it in terms of algebra, and then we can solve a much simpler algebra problem, then it makes our system of thought much more straightforward. And so, all else being equal, if we can do the same thing but do it in a much more simplified manner, then we should obviously do that to save ourselves some time. Okay, and so then Fermat takes Rene Descartes' ideas and he specifically develops them further into a system which more closely resembles what would become known as the Cartesian coordinate system. And then Newton takes both Fermat and Rene Descartes' work, and he invents basically single-handedly calculus and or what would be known as physics, the Physics 1 curriculum that most students have to be introduced to if they do take an engineering course. And so he invents physics and calculus simultaneously by just simply looking at Fermat and Descartes' work and then applying that to the physical world. Now, what's interesting about Newton is that unlike Rene Descartes, Newton actually rejected the notion that there existed a metaphysical reality that explained numbers. Instead, Newton was what is known as a materialist in the sense that he believed the material world was really all that existed or all that we could necessarily prove to exist. His ideas were not as concrete as like pure materialism, but he more or less believed that, if there was some sort of a metaphysical reality, such as a divine creator, the divine creator, such that one should exist, more or less just created reality as a clock and then set the clock into motion. And we are just the pieces of the clock doing their thing. Okay. So he didn't actually believe too very deeply in any sort of deeper reality because he would be the type of individual who would say things like, well, what is knowable beyond what is real? And if you say something is hyper real, what does that mean? Or if you say something is transcendent beyond the real, what does that mean? It's so he would be a person that would really challenge the idea that there is any sort of metaphysical or higher truth beyond the physical world. And so that was one of the major contentions at this point in time that you see between what would become known as the empiricists, or people who believed in empirical thought modes of thought, and this what would be the Rene Descartes faction of people who believed in what is known as neo-platonism. Okay, so simultaneous to Newton, there lived a man named Leibniz, and Leibniz was actually a contemporary of Newton. While Newton lived after Rene Descartes had already passed away, Leibniz was actually a contemporary, meaning he lived at the same time as Newton and was an intellectual adversary of Newton. He actually advocated to put Newton to death to the king of at the time, the king of England, because he felt that Newton was a blasphemer, because Newton's system of physics basically implied that the universe would keep going until it eventually ran out of energy and then it would just die of a heat death, meaning that it would just freeze over. And so Leibniz accuses Newton of basically saying the Bible is false and, being a heretic. And so, like Leibniz and Newton would have this little bit of a spat between one another. Of course, Leibniz independently, what's interesting is he independently invents calculus. Okay. And there's no clue that Leibniz copied Newton's works or that either was even aware of the other's work, except for the fact that they were aware of the other person's theories or other person's ideas of certain subject matter. So Leibniz would have been familiar with, say, Newton's ideas regarding physics, and vice versa. Newton would have been somewhat familiar with some of the ideas that Leibniz had pontificated upon, had talked about. So Leibniz more or less wanted to expand upon the works of Rene Descartes, in addition to, say, working on physics and working on inventing calculus. He really believed very, very strongly in this idea that there was some sort of a metaphysical reality that was beyond the physical world. And so he, in particular, expounded or was a proponent of the idea of what is known as a monad, that there is a fundamental immutable substance that, like atoms, composes these metaphysical things. So he believed that a number one existed in, say, this hyper reality or this transcendent reality, but and then like the atoms that compose the molecules that are, the chemical bonds and everything around us, there would be these things called monads that would be the fundamental substances that would compose these hyper reality things, if you will. And so what is interesting about this monad idea is it's very close, or it's not to say that it's identical, but it is like almost a reinvention of an earlier Christian idea of the ousia, which was, the Greeks, the Eastern Orthodox and the Greeks believed in this primordial substance that made up God himself, called the ousia. And so they, if you read, say, Christian doctrinal texts from the Eastern Orthodox, they will often talk about God as being three hypostasis and one ousia, meaning three states, one primordial substance. Um, so he's taking this idea of the ousia, this primordial substance, and he's attributing that as being almost like an atomic theory of the ousia, which he calls the monad, and he's applying that to these transcendent things, if you will. So either way, regardless of whether Leibniz is correct or Newton's correct, or whatever the case is, um, Leibniz is very famous in asking the question of what is space made of? So like if you have, say, a vacuum that has absolutely nothing in it, what is that thing? What is that that substance that is the vacuum itself, right? Um, Said using the terms of modern physics, when you have a light wave, students will often be aware that light is in fact a wave. It has a certain frequency. There are different frequencies of light, and but what is light waving through? Okay, what exactly is being waved through when light is, when we're measuring that light is in fact a wave, like phenomena? Or people might be aware of electromagnetism and electromagnetic waves. Well, exactly what is waving when an electron is moving? Okay, that's often a question that is not asked by very many people, but it's an important question. And so this idea of like, what is empty space? What is an empty vacuum? There must be something there, to just like a box. A box is a thing, right? It doesn't have anything in it necessarily, but it is a thing. And so the box needs to have space inside of it for things to then fill the box up. But the box itself is a thing. And so he was thinking about this in terms of the vacuum itself being a thing, or empty space being a thing. And so what exactly would that look like? And so then these ideas all eventually coalesce into uh, different a variety of mathematical techniques, which all use the same basic, what is known as a Cartesian plane, in order to represent the geometry of the equations that these different mathematicians would be using to describe whether it be physical reality in the case of Newton, or analytical geometry in the case of Leibniz. And so, what a Cartesian coordinate plane is, and many students will be familiar with this, is it's a plane where you've got four different coordinates. You've got coordinate one being this upper right hand rectangle, or I guess you could say square, if you will. And then if you go counterclockwise around this object, you get to the top left corner, and that is called coordinate plane 2. And then you go down, coordinate plane 3 would be this bottom left corner, and then coordinate plane 4 would be the bottom right corner. And this is to say that we label the coordinate planes in order to describe the behavior of the numbers that exist in that particular plane. So at the top right plane, you have positive numbers going to the left, and you have positive numbers rising into the air here on the vertical axis, or what is labeled the y-axis. And so you could have a phenomena that, say, rises it rises in equal parts to its horizontal displacement. So it's moving upwards at the same amount that it's moving sideways. And so, or maybe it's moving upwards a little bit more than it's moving sideways, or it's moving sideways a little bit more than it's moving upwards. But regardless of the degree to which it's moving sideways or upwards, this would be all described as a positive motion of sorts, or a positive movement. Whereas when you travel into the second coordinate plane, because your x direction is the horizontal line here, the x-axis is now pointed in the opposite direction, we would say that this is a negative direction, or a negative horizontal direction. And so even though an object could be, or an item or a geometry could be represented going up into the sky to the left here, anything going to the left would have a negative horizontal component associated with it. Okay, even though the vertical component would be positive because it's still flying into the sky. So we represent moving upwards as a positive vertical movement. We represent moving to the left as a negative horizontal movement. And when we get down to coordinate 3, we represent moving downwards as a negative vertical movement, but then moving to the left is also negative. So everything in coordinate plane 3 is the exact opposite of everything in coordinate plane 1. So where everything was positive in coordinate plane 1, in coordinate plane 3, everything is then negative. And when you get to coordinate plane 4, you have positive movement in the horizontal direction, but you have negative movement going down into the ground. Okay. Now, regardless of how you decide to represent movement, we may always represent movement in a Cartesian plane. If we want to represent say, movement as a straight line, we can represent that movement using the equation y is equal to mx plus b, where your m is referred to as the slope of a line, your x is the horizontal movement, and your b is what is known as the y-intercept. So it is the point at which your line will cross the y-axis. And each individual point on the graph is, of course, represented as what is known as a Cartesian pair, xy point. So we're going to use this equation, y is equal to mx plus b, and then we will be able to move along the line and represent the movement along the line as a horizontal and vertical component, an x and a y, where x represents how much horizontal distance you've gone along the line, either to the right or to the left. If x is negative, you're going to the left. If x is positive, you're going to the right. And how much vertical movement you've gone along the line by representing y is positive if you're going up, and y is negative if you are going down into the ground. And so with this, we will then move or segue into chapter 3. Take care, guys.